Yeah, can some of you please check whether it is working or not? Yes, it's working. So yeah, you can start.
So good afternoon, everyone. Welcome back. Today is the second day of the 4-day lecture series on Riemann mapping theorem via Dirichlet problem by Professor Diganta Borah. So participants can use the raise hand option if you have any queries. So without delay, I request Professor Borah to start the lecture. Over to you, sir.
Thank you, Kaveri. Okay, so yesterday we stated the Riemann mapping theorem, and also sketch the Riemann's original ideas for the proof. We learned what was the difficulty in his proof. Namely, he was using a Dirichlet problem, solution of the Dirichlet problem on a bounded simply connected domain, piecewise smooth bounded simply connected domain, to construct biholomorphism from the domain to this. But at that time, it was not known if the Dirichlet problem on such domain is solvable. Then we also, recalled the proof due to Caratadori and Kobe using Monte's theorem, and that's where we stop. So our plan now would be to, develop a method for solving the Dirichlet problem, and then try to see the proof using Riemann's ideas. Okay. So let me start with stating what is the Dirichlet problem is. So Dirichlet problem. So this is basically to, we want to find a harmonic function on a domain with prescribed boundary values. Right? So here we will be taking, so let D be a bounded domain in C, and some continuous boundary data is prescribed, and F from delta D to R is continuous, be continuous. Okay, so you so what you want to do? So you have some domain, not the domain we are taking, but it can be still be complicated. And some so from delta D to R, there is some function F is given, continuous. So the problem is to find U such that, or maybe let me write H, find H such that H is harmonic on B, so that is this is Laplacian of S is 0. This is on B, and it takes the boundary values F. It is continuous up to the boundary and takes the H is so what? Let me write it as this limit as Z going to zeta H of Z. So zeta is in the boundary. This is equal to F of zeta. So this statement is basically saying that the function S is continuous up to the boundary, and on the boundary, its values are given by F. This is the Dirichlet problem. Now, it's so this problem actually will not be solvable always. I'll give you a simple example to see this. So let's example. Before that, let me also point out something here. Okay, so see, if a solution exists, then the solution is always unique. It's easy to see. So maybe I write down. So remark: if the solution to solution exists, solution to this problem exists, then it is unique. This is because you see, suppose you have two solutions, H1 and H2. Okay, so what that means, H1 and H2 both are harmonic on D, and they have boundary values F. So these two harmonic functions on D agree on the boundary. But then we know by the maximum principle that they have to be equal, right? So the maximum principle basically says that, so one of its version, it says that if you have a harmonic function on a bounded domain, which is continuous up to the boundary, and on the boundary it is dominated by some constant, then it is dominated by the same constant inside also. So in this case, for example, you can, so if there are two solutions, H1 and H2, so you can look at H1 minus H2, then that will be harmonic inside, and on the boundary it is identically equal to 0. So it has to be not more than 0 inside. The same argument you can apply to H2 minus H1 also, right? So both H1 minus H2 and H2 minus H1 are bounded by 0. So H1 minus H2 has to be 0. Okay. So I guess most of you have seen the maximum principle, but if not, let's not worry about it, because I am anyway going to discuss a proof of maximum principle, because the similar arguments will be required in other results also. So it could be worth revisiting the proof. So I'll do that in some time. So assuming for the moment we know the maximum principle, so then we see that immediately that this solution is unique. So this is by the maximum principle. Principle for harmonic function. Okay, so solution to the Dirichlet problem is always unique if exists. Existence is a problem. So let's see this example. So let me take the following domain. So D be the punctured disk. So D minus 0. So this 0.0 is so the origin is missing from this number. And so let me give you some boundary data. Say maybe say let f of theta, this is equal to, so here I define f to be 0 on the unit circle. So this is 0 when if mod of zeta is 1. And at the origin, so boundary consists of two parts, right? One is this unit circle, and another is this isolated point 0. So here, let me define f to be 1. So if theta is equal to 0. So this function is then continuous, right? Although the values are, so these two pieces values are different, but they are kind of far away. So this function is continuous. So f is continuous on delta D. Now it turns out that this for this boundary data on this domain, there cannot be a solution to the Dirichlet problem. There are various ways to see this. So here is one way to see this. So suppose that there is a solution. So if possible, assume that there is a solution. Solution H to the Dirichlet problem. So then S is harmonic on this punctured disk, and it will have the boundary value F, right? Continuous up to the boundary, and boundary values will be F. Now to derive a contradiction, so let us first observe the following. So we can actually, in this case, determine how H look like, because you see the domain is very nice. It is just the punctured disk, and the boundary data. If you look at the boundary data, it is actually a radial function, right? So radial means it depends only on the absolute values. So you take a point, say, here or here, it doesn't matter. The value is same. So the value is constant on circles centered, etc. So this boundary data is circle. In this case, it turns out that boundary data is radial. It turns out that the solution also has to be radial. So let's see why that is the case. So my claim is that H is radial. This basically means that H of Z is same as H of mod Z. So on a particular circle centered at 0, the value is actually constant. Or another, so another way to say this, that is H of Z, it is actually rotation invariant. So H of Z is same as H of the e power it Z for all P in R. Okay, so for all. So this is for all P in R and Z in D. So let's see why that is the case. This is again easy to see. You see, so what I do is let's go to the next page. So what do we have now? Yeah, we want to see that the H is rotation invariant, right? So let's do the following. So let's consider another function. So let say V be the function. V of Z is basically H of e power it Z. So you're fixing a T. So let's fix so fix some T and fix T in R and consider this function. What can we say about this function? Well, you see, this is basically composition of two functions, right? One is this function. So this e power it Z. So Z going to e power it Z. So this is basically a multiplication by this constant e power it. T is fixed, right? So it's a multiplication by this constant. And second part is this you are composing with this harmonic function H to get H of e power it Z. So this multiplication by e power it, that is because multiplication by constant, so it is a holomorphic function. So this part is holomorphic, and this part is harmonic. One can easily check that composition of harmonic function with a holomorphic function is always harmonic. So this composition is easy exercise. Okay, so I leave it as an exercise. This is harmonic. This is harmonic on D. And clearly it is also continuous up to the boundary because H is so, right? E power it Z is not a problem anyway. So what are the boundary values? Well, boundary values, you see, if mod Z is 1, then mod of e power I t z is also 1. And so h of e power I t z, so what is the boundary value on the circle I took? 0. 0 on the unit circle, 1 at the center. So h is 0 here. Okay, so that means v is 0. So v on the unit circle is 0. What about at the center? Well, center, so if z is 0, again e power I t z is 0, h0 is 1. So if z is equal to 0, similarly v of 0 is. So this function v also have the same boundary values, right? V is a harmonic function with boundary value f. So this is also a solution to the Dirichlet problem, but we have seen that the solution is unique, right? So v and h are same. So v is also a solution, and hence by uniqueness, v is equal to h, right? So what you have proved that so this implies that h of e power I t z is equal to hz. Right? This is true for all z. T is fixed, but then you can work with different t also. You get the same result, right? So therefore, this proves that h is radial. So my claim is established now. H is a radial function. Good. Now, once I know that h is radial, you can very easily write down how h look like. So for this, you recall that recall from your calculus course that in polar coordinates, the Laplacian has a particular form, right? So in polar coordinates, so the Laplacian looks like 1 upon r, and then ddr of 1 upon r into ddr, and then the other part is 1 upon r square, d square, d theta square, right? Yeah. So this can be easily checked, okay? So by a chain rule. So I leave it to you to verify if you don't remember. So, but once you know this, and you also know that h is radial, right, as a function of r theta. So if you write z is equal to r e power I theta, so h actually does not depend on theta. It only depends on the r. So now from there, so can you now, why don't we take a minute or so to see how it's look like? Okay, so it would be a good exercise. So can you just do a computation, simple computation, to help me to write down what is h? Why don't you take a minute and see? Maybe one of you can, if you can tell me the answer, that would be good. I'll take a break, 1 minute break. So the question is clear, right? I want to write the function h, the form of the function h. What I know that it is independent of theta and it satisfies Laplacian of h is 0, and Laplacian is given by this the formula here. No one would like to speak? Okay, no problem. You see, as h is independent of theta, so you don't have to worry about this part. right? So we have basically 1 upon r. So 1 upon r ddr, 1 upon r dh dr. This is 0, right? This part, the second part anyway is 0. So this gives that, so 1 upon r, you can multiply both sides. And then because ddr of this guy is 0, so this has to be, some, so anyway, it is independent of theta. So it has to be some function of some constant, right? So it has to be something like a. So derivative is 0, so it has to be some constant. So you have dh dr is equal to r times a. So right. So this gives that h is of the form. I do some. So this has to be of the form log r plus, but looks like I am doing so. This let me see. So dh dr a by r. So I probably have done it. So this should be probably r. Okay, so I think this is a mistake. And maybe because of that, you were probably not. So I know the solution needs to be look like this. So if h is a log r plus b, so dh dr should be a by r, not a. So sorry, yeah.
One student has
All right.
raised hand.
Yeah.
Byron?
Somehow.
Sir, excuse me.
Yeah.
Sir, you said H is independent of theta.
Yeah. So all this already I am sure that S is independent of theta. So here theta will not come into it. So it is basically an OD that is you are trying to solve now. Okay. So A is just a constant. Yeah. Okay. So H has to be of this form finally. But now is that possible? Let's see the boundary data. So when mod z is 1, so that means r is 1. So this first term is 0. So that means h is 0, and this so log r is also 0. So b is equal to 0, right? On the circle, it is given to be 0. So b has to be 0. So h is now of the form a times log r. But what about the other boundary data? So if now z goes to 0, so this cannot be bounded, right? So this is unbounded at 0 unless a is 0. But the solution, as we have said, has to be kind of continuous up to the boundary. It's bounded, right? So you are forced to take. So a is also 0. So a is also 0. But then it implies that s is identically equal to 0. This is again a contradiction because this contradicts h0 is equal to 1. Right? So you cannot have a solution to the Dirichlet problem for the punctured disk with the given boundary data. Okay, so the Dirichlet problem need not be always solvable. So let me give a definition here. So I'll say that if the Dirichlet problem if the Dirichlet problem on D, on a domain D, D is solvable for all continuous boundary data, then we say that the Dirichlet problem on D is solvable. So solvable means it has to be solvable for all data, or there is simply a Dirichlet region. We say that D is a Dirichlet region, or the Dirichlet problem. We say that the Dirichlet problem on D is solvable. So when I say solvable, it has to be solvable for all boundary data. So the previous example is not a Dirichlet region. Okay, but we also know there are many domains where you can always solve the Dirichlet problem. Right. So, for example, you must have seen how to solve the Dirichlet problem in a disk. So this is well known, but I'll still recall at least the formulas. So this is Poisson integral formula. So some consequences of Poisson integral formula. So let's quickly recall the Poisson integral formula. So let's first do it for the unit disk. This is the Poisson kernel. For the unit disk D is the function. So it's a function of two variables. I'll denote it by PD. It's a function of two variables. The first coordinate is coming from the disk, and the second variable comes from the unit circle. It's a real valued function. It's given by, so z zeta, this is real part of zeta plus z, zeta minus z, right? So this is how we define the Poisson kernel. You can simplify this. Actually, what you can do, so this is real part of this complex number. You can write it as half of this plus its conjugate, right? So if you do that, so in the denominator you have zeta minus z in one of the this quotient, and the another it will have zeta minus z bar, right? So denominator will become zeta minus z square, and so there is a half here. So in the numerator you will have now two terms. One is zeta plus z into conjugate of zeta minus z. So that will give you mod of zeta square minus so zeta into you will have z bar, and then you have z into zeta bar, and then minus mod z square. So this will be the first term, and the second term. So let's get some space here. The second term is going to be something similar. So many of the terms will get cancelled here actually. So the second term is going to be zeta bar plus z bar into zeta minus z, right? So you have mod of zeta square once again. And then you have, so the second term, zeta bar into zeta bar into minus z. And then, so you have z bar into zeta and minus mod z square. So some of the terms will get cancelled. You see this term, mixed terms, zeta z bar. So this terms gets cancelled with this and the other also, right? And mod of zeta, because it is coming from the boundary, so it is 1. So this takes the form now. So there are 1 plus 1, 2. There is a half, so I just write it 1 and minus 2 mod z square. So 2 gets away. So that's this. Okay, so the Poisson kernel looks like this. You can also, sometimes it is good to write in terms of this polar coordinate. So if I write P D, so Z is R e power I theta, and zeta is e power I t, then this takes the form 1 minus R square and divided by mod of e power I t minus this is R e power I theta square. Okay. Good. So this is the Poisson kernel, and the Poisson integral of a function is defined as follows. So if f from delta d to r is continuous, then so the Poisson integral, so I'll denote it by p a d f z. So this is defined as, so you are going to integrate. So let's first, so there will be certain constants. So you basically want to take integrate over the boundary of the unit circle. I'll put a 1 by 2 pi I here. This Poisson kernel PD z comma zeta, and then you have f of zeta d zeta. So you are integrating f, this boundary function, with respect to the Poisson kernel. But it would be good to write in terms of parameterization. So if you parameterize this unit circle as e power I theta, e power I t, so then so this becomes so this will be 0 to 2 pi. 1 upon 2 pi, this I will cancel because d zeta will have an I there, right? So this is going to be PD z e power I t f of e power I t and so the Poisson integral of f is given by this integral. It would be good to remember. We'll be using it again and again. Now, so see, you can see the following. So PD is given by real part of something, right? If you look at, so our earlier definition was, so if you look at this part here, this real part of something, that something is actually a holomorphic function of z, right? So this guy is actually a real part of e power I t plus z and e power I t minus z. F is a real valued function. So you can actually take this real part out of the integral. This is f is real, this guy is real. So the real part comes out of the integral, and then what is left is, so it's actually, 1 upon 2 pi real part of certain things, which looks like e power I t plus z, e power I t minus z into f of e power I t. So you are integrating out this t variable, and as a function of z, it is holomorphic. So the result is holomorphic, and then you are taking real part of a holomorphic function. So this has to be, so this guy is holomorphic, and the real part of a holomorphic function is harmonic. So this Poisson integral is clearly a harmonic function. Okay, but more is true. What it happens is that the boundary values turns out to be exactly f. that requires some work. So we'll not go into the detail because this is usually discussed in a complex analysis course. But I nevertheless want to write down this as a theorem. So let f be a continuous function on the boundary of the unit disk, real value. So real value for the moment, but you can also work with complex value by separating the real and imaginary parts. But let's just work with real value continuous function on the boundary of the then Poisson integral of f is harmonic on B. This we just have seen, and it also has boundary value set. So and limit z going to say zeta PDF. This part requires some amount of work. Okay, you have to examine certain properties of the Poisson kernel. So maybe I'll write down a set of exercises. You can recall how we show this. Right. Basically, you have to understand that the Poisson kernel that this actually gives a approximation to identity. Okay, so one needs to go through the calculation. So we'll maybe I'll prescribe a set of exercise for that, but we'll assume that this is true, which is usually done in a complex analysis course. Okay, good. So this tells you that on the disk we have this on the unit disk, the Dirichlet problem is always solvable, right? You start with any continuous boundary data, then simply you have to take the Poisson integral. You can do this for any disk actually, so not necessarily the unit disk, because so if you have say, some disk. You have any disk centered at Z0, radius R, then I can always go from disk to the unit disk by means of an affine map. So this is you simply look at the map. So you have to translate a dialect. Z you have to Z0 bring you have to bring Z0 to the center. So you basically look at Z minus Z0 and divide by R, right? So this map will take this disk to the unit disk, take the boundary also to the boundary. So what you can do now, given a continuous function on the boundary of this disk centered at Z0, say some boundary data is given here, F. Then you can push this function to the unit disk. You simply look at F40 inverse, right? So you will have then, so this function F40 inverse, T is going to the unit disk. So you have to look at F40 inverse. That will be a boundary data on the unit disk. So then you solve the Dirichlet problem there. So you basically will be looking at the Poisson integral, this guy, right? This will give you a harmonic function on the unit disk. So you want to again come back to the original disk, right? So you have to again use the map. So you have to look at this. You have to evaluate it TZ, right? If you start with Z in the bigger disk, this disk is Z0, so you can go to the unit disk by means of T. You have solved already there, PD F40 inverse, and you just have to look at. So this will be the solution. It will be good to actually write. So I write down the formula how it looks like. So but I leave the verification for you. So as a theorem again, I will state it. So let FVA real valued continuous function on the disk centered at 0, Z0, radius r. Then, so I'll denote this, the result will turn out to be the following. So you'll have something like this, 1 upon 2 pi, 0 to 2 pi. So you'll have the Poisson kernel for the disk. But the points are basically, you are coming from, say, an arbitrary point here, looks like Z0 plus, say, R e power I theta. So you are trying to write down the value of H at Z0 plus R e power I theta. So you have to go to the unit disk by means of T. So that would look like Z minus Z0 by right. Z is this guy. So that will be, so this is your Z. So Z minus Z0 will be this small r e power I theta, but you have to divide it by capital R. So this is R by R e power I theta. And then if you take a boundary point, so boundary point here looks like Z0 plus R e power I theta. So small r is capital R here. So basically you will have only e power I theta. And the boundary function F was on the boundary on the left circle, but you have to go to the unit disk, right? So this point goes to Z minus Z0. So this is basically, you have Z0 plus, because T inverse you have to look at. So Z0 plus, so if you start with something here, e power I theta, e power I t here, and then e power I t comes to Z0 plus R e power I t. This is the boundary dt. Don't have enough space for here, so you have the d. So this integral I will denote it by, you know, the Poisson integral. Sorry, Poisson, Poisson integral. I'll call it Poisson integral on the disk of radius r, center z. So I'll denote it by this thing. So this is so you can check so you, when you try to write down, you will see that this box here. So you will see that this function h is exactly. So this is the Poisson integral of f on the on an arbitrary disk. So this again, this solves the problem. Okay, so then this is harmonic on, and it also takes the boundary value f. So this, if you take limit that going to zeta, this is f of zeta. All right. So we have now, so every disk is a Dirichlet region. So you can solve the Dirichlet problem on the disk. So there are several consequences of this fact. So I want to, recall some of them. This will eventually help us to, solve the Dirichlet problem on an arbitrary domain. So let's go through these properties. Okay. So any question? Right. We'll take a break in few minutes, but let me write down a few properties first. So, so corollary. So this is the Poisson integral formula. So this is kind of what I'm going to write is kind of an analog of Cauchy integral formula. So Cauchy integral formula for holomorphic function says that you can recover the function in a disk by integrating it on the boundary with respect to the cosecant. So here, for the analog for the harmonic function says that you can recover a harmonic function on a disk by integrating it with respect to the Poisson kernel. Right. So this is how it looks like. So let H be a harmonic function. Say in a neighborhood of say some disk. In the neighborhood of the closure of the disk. So there is some open set where it is harmonic, and that open set contains this closure of the disk. So this is Z naught. So you are in some neighborhood of this, maybe some, maybe I. So this is harmonic on this vision. Then the claim is that then you take any point. Basically, you want to say that H is then H is equal to the Poisson integral of so that H is equal to the Poisson integral of the boundary values of H. So let's write on the Z naught R of so the boundary function. I'll take the boundary values of H on the Z naught R. So these two functions are equal. So on the left you have this harmonic function. On the right you see I am looking at the values of H on the circle, and then looking at the Poisson integral of that boundary values, and I am saying that both are equal. This is because you see, if you look at, what we have just seen is that the right hand side, this guy, this is because this guy is. So if the right hand side is, we just have seen that solution, because this is a harmonic function with boundary values H. So this is solution to the Dirichlet problem on the Z naught R with boundary data, this, right? by what we have just stated. But on the other hand, H is also a solution, right? H is harmonic in a neighborhood of this disk, so it is already harmonic there, and boundary values are H itself. So this also is this guy also is a solution to the same Dirichlet problem. So by the uniqueness, they have to be equal, right? That's it. So no need to write a separate proof. So this follows from the uniqueness to the solution of the Dirichlet problem. Right. So this this is basically as analog of the Cauchy integral form, because the right hand side is kind of you are integrating the function H on the boundary of the circle with respect to this Poisson kernel, right? An immediate consequence of this is the mean value property. So what I do is, so if you look at, so on the same, so under the same hypothesis as this, so let's write down what is H of Z naught. So value at the center. So you have to write down what is PD Z naught R H restricted to the boundary, and you want to evaluate that Z naught. But if you look at the Poisson integral formula, so let's go back to the previous slide and see how the value looks like at the center. So here is it. So let's look at this guy here, this formula. So I'm taking now, so I'm evaluating at Z0, right? So R is basically 0, small r is 0. Then what you have is that, so this part, the first argument in this PD will be 0, right? So P of 0 comma e power it. The rest of the part is fine. That is not a that will be this is as it is. But here you have PD of, so this will become 0. But if the first argument is 0, so where is the Poisson kernel formula? So it is here. So let's see what happens to the Poisson kernel if we take Z is equal to 0. For Z is equal to 0, you see this is real part of zeta by zeta, real part of 1, which is 1. Right? The Poisson kernel is 1. So you can see it from here also. So when the first argument is 0, the Poisson kernel is irrespective of whatever the second argument, it is identically equal to 1. So this will be, so when you put the first argument to be 0, so it is 1. So what we have now is simply, so this is simply, again, I am running out of space. So this is equal to 0 to 2 pi. So the Poisson kernel part becomes 1. So what you have only Z0 plus R the power it. Right. So this is nothing but, you see, this integral. So you are integrating f on the boundary circle, and you are recovering. Oh, so why f is coming? So it should be h. So now my function is h. So I should write h here. So if you integrate h on a circle, it reproduces h at the center. So this integral is basically, you see, the average of h on the circle, this circle of center Z0 and radius r. So average or mean. So that's why it's called mean value form. So this is mean value property. Mean value property. All right. Good. Okay, so maybe I would take a break here for a few minutes. If you have some questions, you can please feel free to ask.
Yeah, so the break is till 4 p.m.
Yes, Nitin.
Sir, can you please tell me what is the physical meaning of Poisson integral? Like I said, like we do integral in a real, and that means it is the area under the curve. And what is that like this? What is physical meaning?
I don't know how to put that. What exactly you are trying to understand by physical meaning here?
The geometrical interpretation like this. Just for example, in real, if you do integration, that means it is the area under the curve. So like this is physical meaning.
No, I don't have words to. Yeah, I don't know how to say that. Yeah, sorry. Yeah, but it's like, the same as I say, the Cauchy. So if you want the motivation, it is similar to kind of Cauchy integral formula for holomorphic functions. There you have the Cauchy kernel. Here you have the Poisson kernel. So I would still suggest, so there is some motivation in the Alphonse book. Long back I studied, but I don't remember now. There is some, interpretation for how to arrive at this. Nice interpretation. So do have a look at Alphonse book. There is something. Maybe that will satisfy you. Yeah.
Okay. Okay, sir. Thank you.
Okay. Yeah. So it is, if I remember correctly, it is like, so you uh, basically want to solve the heat equation, or so with some data, and they come up with some motivation like that. You should definitely check that. Yeah, that's a good question.
Okay. Sir. Okay. Thank you, sir.
Right, right. Yeah.
Sir, can you please
Yes.
explain once again that how we are going from arbitrary disk to a unit disk, that composition thing?
Yes. Yes. That will be a nice exercise to actually try. So if you look at this picture under this unit disk on the disk on the right, I know how to solve the Dirichlet problem, right? Now, for an
Yes.
arbitrary disk centered at Z0, radius is capital R. So you look at this map, this T. Hey, this is an affine wave. Define every occurrence, Z minus Z0 by R. So this will take this disk to unit disk, right? If Z minus Z0, mod of Z minus Z0 is strictly less than R, mod of Z minus Z0 by R is strictly less than 1. So you will be, once you apply T, so if Z is here, TZ will be here. Okay, in fact, TZ is going to be exactly what I have written here. So, and the boundary data is given on the left. So you want a boundary data here. So this, you have to look at the function FO T inverse, right? Because you want a function on the boundary of the unit circle. What is given is this F on this another circle. So from the unit circle, you go to the other circle and compose with F. So that is like F of T inverse. T is coming to the right, left to right. T inverse is from left, right to left, right? So F of T inverse is the boundary data. That's why I'm solving the Poisson, writing the Poisson kernel, Poisson integral of this boundary data. So this gives you a solution on the unit disk, but you want a solution on the original disk, right? So you have to look at the evaluated TZ. So H at Z is equal to the Poisson integral of F of T inverse evaluated at TZ. Okay, so this is going to give you the solution, because you see, we have already seen, if you have a harmonic function and you compose with a holomorphic function, here T is the holomorphic function, so result is a holomorphic function, right? So that tells you that this H is a harmonic function, and the boundary values also easily you can see that it will be F, because the function is kind of, T is kind of linear, right? It's just an affine, nothing will be destroyed here. This is going to this kind, so on. And you can, once you write down the explicit form, you will see that it turns out to be exactly this. Okay, so you should definitely try this exercise. It's just a, rewriting in other coordinates, so it's not difficult. You should try that.
Okay, sir. And one more thing, is converse of mean value properties, is it true?
Yeah, I'm going to discuss this. Yes. Yeah, that is also true. Yeah.
Okay, and sir, one more question, maybe that one be silly. Like we define a Poisson kernel, like there is a name of like kernel, so I'm relating like a linear transformation.
Yeah,
then we can define a kernel. So is it like,
Oh,
can we
no,
deduce?
No, not in like that. So you mean a kernel for like linear maps or homomorphisms kind of thing, right? No, it's not like that. Yeah. No, that's that's a different kernel. That is kernel of a map, that is a set. Here we call it kernel because we integrate with respect to kernel, we recover something.
Okay.
Yeah.
Okay.
Right. Okay. Our break is over, so maybe we can resume. Yeah, so so here's a beautiful consequence of the mean value property, the so-called maximum principle. So let me. There are several versions. So here is one version that we can state. So let D be a domain. So let H be a harmonic function. On a domain D, any domain, okay, no need to assume bounded or something. So this is just the domain. H is a harmonic function, and say H is less equal to H of Z is less equal to M on for all Z. It's bounded by M, bounded above by M. Okay. So H is bounded above by M on this domain. If it happens that if H of Z naught is equal to M for some Z naught in D, so that means now M is the maximum, right? So H is achieving its maximum at some point in the domain, interior point. So then it turns out that then H is constant, it's identically equal to for all Z in D. So if a harmonic function attains its maximum at some point in the domain, then it has to be constant. So the domain is important here. Connectedness is important. Okay, so when I say domain, it's yesterday I said open and connected. This is easy to see actually. So how do we do that? So the reason I am recalling this proof is that the same argument I'll be using several times in the future also to prove another result. So as I said, it's worth revisiting the proof. Okay, so you know that at some point the value is M and you want to show that everywhere it is same. So you look at the following set. So let A to be the following set. Z in D says that HZ is equal to M, right? What you want to show that this A is the all set D, right? A is equal to D. That's what you want to prove because you want to show that H is equal to M everywhere. What you know at this moment is the following. A is non-empty, right? As Z naught is given to be in A. And you also know something. H is a continuous function, right? Because it's a harmonic function. So it's a continuous function. So H equal to M is a closed subset of D. So A is a closed subset of D. What I'll do, so my claim is that A is also an open subset of D. And if I verify this claim, I am done, right? Because D is a connected set and you have a non-empty set A, which is both open and closed. It has to be all of D, right? So the moment I verify this claim, the proof, since the D is connected, this would imply A is all of D. So this will complete the proof. All I have to see is that A is open subset of D. Okay, how do I prove something is open? If you pick up something, you have to show that there is a neighborhood of that point, which is there. Okay, let's draw some picture. say here is your domain, and some set you have considered. So that set contains the point Z now. I am trying to show that that set is all of this, but I don't know how it looks like. So let's not draw that set, but what I am taking some point, say, let's call it what, maybe some W. So W is in A. So let W is in the set A. Okay, so I want to produce a neighborhood of W, which is also in A. So what do I do? So what I know is that if I take any disk around W, which is in the domain, so maybe let's make the domain a little bit complicated. It might have certain gaps and all. These things. So what I know, if I can draw a disk around this point, which is inside the domain, something like this. Then I know that because H is harmonic in the neighborhood of this disk, the mean value property will hold for this disk, right? On the if you integrate on this red circle, you will get back the function at W. You can do something more. In fact, you take now, if you know the moment you know that some disk is here. So if you draw another disk inside it, there also the mean value theorem holds. Right? That is another disk which is inside the domain where the function is holomorphic in a neighborhood. So on that circle, the green circle also, the mean value theorem will hold. In fact, you take any smaller circle, subcircle, there also the same thing is going to hold. So what I say, by mean value theorem. So let's write in short, okay, by mean value theorem. So I'll write in MVT for short. So there exists epsilon greater than 0 such that you take any so this is R. So this you take any R between 0 and epsilon. So there, this main value property is going to be true. F of W is equal to 1 upon 2 pi integration 0 to 2 pi. So I think I took the function as H, no, not F. So let's write H. So this is H W plus R e power IT. D. Right? For all these circles, the mean value theorem holds. Okay, so my idea is to show that this red disk is inside. So we show that the disk centered at 0, comma epsilon. This is the E. Okay, that means the function is constant equal to M on this entire disk. That will prove that this set is open. To see this, so what you do? So how do I show that it is constant on the whole disk? So basically, let's focus our attention on this one particular circle. So the green circle. Yeah. So this let's look at, so I'll show that on every circle like this, the function is constant equal to M. So the mean value, so this equality here, remember H at W, I am assuming this value to be M, right? So let's rewrite this equality for this R. So note that. So this we have. So if I bring, so let's do some calculation here. So this constant. So the left hand side you have this constant M. I can write it as 1 upon 2 pi integration 0 to 2 pi m dt. Right, m is just a constant. It will come out. This integral is t. That is 2 pi gets cancelled. So I'm writing m in this way so that I want to combine both. Right hand side you have an integral, left hand side you have a number. I'm writing it in the form of integral and I want to combine. So then this becomes, so if you call this say star by star, so I bring the right hand side to the left hand side. So then I have 1 upon 2 pi integration 0 to 2 pi m minus h of w plus r e power I t and dt. This is equal to 0. Right? This is, I'm just rewriting this equation star. Good. Now look at the integrand. What can we say about the integrand? Well, if you recall, m was the maximum, right? H is less equal to m everywhere. That I know. So this integrand is actually, this is a non-negative. This guy is non-negative. So you are integrating a non-negative function on this interval 0 to 2 pi, which is 0. So the function itself has to be 0, right? Because if it is non-zero somewhere, it will be non-zero in a length interval of positive length. Then this integral will also be positive, right? So we know this fact. So if you integral of a non-negative function is 0, the function has to be 0. So therefore, so h of w plus r e power I, this is a function of t. So e power I t, this is equal to f. This is true for all t now. 0 is less equal to t is less equal to 2 pi. So this shows that this function h is constant on this green circle, right? This entire circle. But remember, this r is, we are allowed to take r to be anything. So this is also there already. So for each r, we have shown this. Okay. But if you take, r and t, now you are allowed to vary. So what you are getting, you are basically showing that for every point, so on this red disk, the function is equal to m. Right? So this implies s is equal to m on this red disk. So the centered at w radius. Therefore, we are right here. So therefore, I have proved that this, this is an A and say so. And as I said, because we are walking in a connected set, now A has to be all of the set. So this proves the maximum principle. Right? So you have a continuous function on, harmonic function on any domain. If it is less equal to m and if it's equal to m some point, it has to be constant. So let's write down. So one remark here. So this will be an important remark. See, in this proof, what are the properties of harmonic function I used? If you check carefully, I have used the mean value property and continuity, nothing more than that. Continuity is also, all these integrals and all, they make sense. And the mean value, mainly the mean value property, that is what is important for us. So nothing else I have used, no other property of harmonic function used, right? If you look at the calculation on this side, it's entirely based on the mean value property. So if you know that given a point say w, you don't even have to know that the mean value property holds for all circles centered at w. But if you know that all small circles, that is good enough. If you know the mean value property for circles like this, so there is an epsilon, and for all r less than epsilon, the mean value property holds. That is the only property you are using here. So the same proof shows that. So the arguments in this proof shows that the maximum principle holds for any continuous function that has mean value property. In fact, local mean value property that has local. I'll explain. I already explained. So you don't have to know that the mean value property holds on all circles, but sufficiently small circles. It has local mean value property. So what does it mean? It means given W in D, there exists some epsilon greater than 0, such that the star on holes, that is such that H of W is equal to 1 upon 2 pi 0 to 2 pi or I. So whenever R is less than epsilon. So for all small circles, if the mean value property holds at every point, then the same argument shows that the function will satisfy maximum principle. So I'm going to use this fact to show that the converse of the mean value property also holds in a moment. But before that, I need to point out a few more consequences of this maximum principle. So here is one. So corollary. So version of the maximum principle that we used in the beginning is the following. So let D be a bounded domain and H a harmonic function on B that is continuous up to the boundary, that is continuous on D bar. Then the following holds. See, because you are assuming that H is continuous on this closure of the bounded set, which is a compact set, right? H is now continuous on this compact set D bar. We know that there is definitely some maximum, right? Maximum is somewhere. It attains its maximum somewhere. The thing is that if it is attained in the interior, then the previous theorem says that the function is constant. So that means the maximum is attained everywhere. It is equal to constant, right? And if not, so if it is not constant, then by the previous theorem, the maximum has to be on the boundary. So both the cases, the following holds. So maximum of, sorry, what happened? Yeah. So if you look at the maximum of this function on D bar, this is definitely there. So we have considered two cases. One, when the function is constant, the maximum is then everywhere. And if it is not constant, it is only on the boundary. So in both the cases, therefore, the following holds. So you can simply look at on the boundary. So you want to determine the maximum, it is enough to look at the boundary. You don't have to look at everywhere. Okay. And this also tells you that if suppose H is less equal to M on the boundary, then H is less equal to M on D also. This is simply from 1. You see, the right hand side is dominated by M, but then left hand side also has to be dominated by M, right? So if on the boundary H is dominated by M, so it has to be dominated by M inside also. This is the version we are using. Good. Now, so let's talk about this important that confers to this mean value property. So I'll call it as a theorem. So this is converse to the mean value property. So what it says that, so let H be a continuous function. Continuous function on a domain D, and suppose that H has local mean value property. Okay, so we says that, recall this says that is if given some point W in D, there exists epsilon greater than 0, such that H at W is average of H on sufficiently small circles. So W plus R equal I. P. This is true for all R less than epsilon. So local, because you don't have to, so you are not assuming that it has to be true for all circles inside D, but sufficiently small circles, that is good enough. So then H is harmonic on D. The proof is not difficult. You have to, make a guess. How do I show that? So basically, I'll show that H is equal to some harmonic function. In natural, see if H is harmonic, then we know that it has to be equal to its Poisson integral, right? We have by Poisson integral formula. So that is the aim. So, so you show that it is equal to its Poisson integral everywhere. Okay, so, and because harmonicity is a local property, so you want to show that some H is harmonic on D, it is enough to show that on each open disk it is harmonic, right? So what you do, so let so let some disk is there. So suppose some disk, let's delta equal to some disk. So let's simplify our notations. So this is a disk inside, and so delta bar is inside, say, D. I'll show that H is harmonic on delta. So my claim is that H is equal to the Poisson integral of this on delta. So you have some, so you have this domain, and what you are seeing that, look at a disk here. It's an arbitrary disk centered at Z naught and radius R. So I can talk about, because H is a continuous, so I can talk about the Poisson integral of H on this, and I'm saying that is equal to H itself. So because the right hand side is harmonic, so this will imply that the left hand side H is also harmonic. So this once I verify the claim, I'm done, right? How do I check this? to check this. So you look at, so consider the following function. K is equal to, so you look at the difference of these two functions on delta, and on the boundary you take to be 0. What can we say about this function? Certainly it is continuous, right? Because both h and the Poisson integral is harmonic, so it is continuous. So this h minus the Poisson integral, that is a continuous function, right? Both of them has mean value property. H has mean value property, that is given. Poisson integral being harmonic has mean value property. So difference also will have mean value property. So the function k, so this is a continuous function with mean value property. And we have already remarked that if a continuous function has mean value property, local mean value property, that's good enough. Then you can immediately say that it will satisfy the maximum principle. So this guy, this has mean value property, local mean value property. So we know that it satisfies the maximum principle, but on the boundary you see it is 0, and so it has to be so by maximum principle. So k is equal to 0 on delta. That, but k being 0 is same as h is equal to delta. So this verifies my claim, and hence, as I say, now h is harmonic on this this delta, and this is true for all this, right? So this proves the this converse to the mean value property. I still have 1 minute. I will write down a corollary to this and stop. So the corollary is something like in complex analysis, we know that if you have a sequence of holomorphic function that converges locally uniformly, that is uniformly on compact subsets, then the limit is also holomorphic, right? The same is true for harmonic functions. This is because, so as a corollary, let me write down. So let Hn be a sequence of harmonic functions on a domain D that converges locally uniformly, that is uniformly on compact subsets of D to a function H. Then you see, because it is uniform limit and H's are continuous, so H has to be continuous. Moreover, each Hn satisfies the local mean value property. So now integral along circles, because you are assuming that convergence happens, uniform convergence happens on compact sets. So if you take a circle, so integral of H1 on circle will converge to integral of H on that circle, right? So on the left you have the mean value property, and hence H will also have the mean value property. Okay, so then H is continuous and has mean value property, and just what we have seen implies that then H is harmonic. Okay, so we have already, I have already outlined how to prove this. Okay, so I'll stop here. If you have any questions, please ask. Yes, Nirmala, not Nirmal, yeah.
Yeah, sir, in the proof of converse mean value theorem from the statement, how can we sure that the second partial derivative will be exist? Like we didn't demand anything for that.
Yeah, no,
We just
right,
demanded
right. Yes, we don't need because we have shown that. You see,
in the proof it
I
is
have
clear.
shown that. Okay. So proof I have shown that it is equal to some harmonic function, right?
Okay.
Because this guy is harmonic. So I am showing that this continuous function is equal to some harmonic function locally. That's good enough. So then it's already like the C2 smoothness and all follows. In fact, harmonic functions are actually infinitely smooth. They're real analytic. Something more, but we won't go into that. Right? Yeah.
Okay.
So you don't have
Sir,
to.
and
Yeah.
yeah,
Yes,
and
go.
the corollary of the above corollary on the next page. Next page, is it something like a Harnack's theorem?
And no, Harnack's theorem. Yeah, so we'll do something like Harnack's theorem. This is saying that if you know that the sequence converges, then the limit is harmonic. Okay, but Harnack's theorem is something like it gives a condition under which it will converge, right?
Okay.
So it says that if family is locally uniformly bounded, then you will have a subsequence which will converge. We'll do a analog of this for harmonic functions also. Takes time. Okay. Yeah.
Okay. Thank you, sir.
Yes. Any other question? All right, we can then stop here. I'll yes, if this.
No, sir, you can continue.
No, I just wanted to say that I'll write down the set of exercises. Maybe you can share with the participant. And maybe if they need some help to solve it, we can have some extra session sometime during the week. Okay. Or some volunteers might also help, whatever.
Okay, sir. If there are no further questions, let's thank Professor Borah for this wonderful talk. And I also thank the participants for the active participation. Now, our next session is on 10th September at 3 p.m. The Zoom link is the same.
Yeah, thank you. So let me stop the recording.